So let's recall where we were last Tuesday. We have seen a lemma which underlines a particular step in one of the proofs of Masque's theorem, which tells us that if you have any two representations, linear representations for a group G, and you have a linear map, any linear map, then the map F prime, which you can build by well, it's not an average, but by taking this sum over the group, is a morphism representation, meaning that say a row one entering on well, let's use a row one entering on this side, X is at the two on the other side, and I mean the fact that here you have G and here you have G inverse ensures that we can do that. So this allows us to start from any linear map F and build a morphism of representations. Why is this important? Because we know from Schur's lemma that there isn't much in terms of morphism representations when two irreducible representations are not isomorphic. And even if to have two isomorphic representations, then a morphism representation can only be a multiplication by a scalar. So it's very limited. I mean, the F prime that you can get from this construction are limited from the result we've seen. And so the first result we've seen tells you that you have two irreducible representations which are not isomorphic. At first I had forgotten to add the reducible clause. Then you consider, well, yeah, you consider them as being the space of row vectors with basis, the U basis for V1 and the V basis for V2. And this, I mean, so the representations are row one and row two, okay? So the index denotes which representation you're taking. So you use exponent to denote not powers, but the JK component of the matrix rho I of G. And then for all indices between I and N, yes, well, no, it's, okay, but say this from one to N and this from 1 to M, depending on which space you are in, you have this this thing in which you multiply you sum over G this multiplication, and you always get 0. Okay. Note that if you take this basis to be basis with respect to which the representations are unitary, okay, then you can change this because in that case you have that you have that if say row one is unitary, let's write it here with respect to this basis, then the row one of G inverse won't be anything else what row one G transpose conjugate, okay? Because that's the adjoint of with respect to a standard basis, with respect to this, yes, to this basis. And so in particular, you will have that this row one JS G inverse will be row one of G Sj, I've taken the transpose conjugate, okay? So if this is unitary with respect to this basis, then you have this fact. And we employ this fact when we have a single irreducible representation, more about this later. So suppose you have a basis, and let's add with respect to which the values rho G are unitary. Then we play this trick, and so here we might have written, and it would be correct, rho JS, and this is what we will obtain, in fact, but we write instead rho SJG conjugate, okay? And in this case, when you have a single irreducible representation, then the result, well, it's a single representation. So there's only one space of dimension, say, n. So the indices run from 1 to n. And then you have that this is usually 0, unless the indices are exactly the same. So S equals T and J equal L. Okay. And then you get the order of G divided by n, the dimension of B. Okay, so let's see how you prove this. Okay, to prove this, we consider first EST. Well, let's define EST as usual. So let me check the notation. Yes, the basis is U1, UN. So this is the vectors, the linear map from B to V. We sense US to UT and U whatever I to 0 if I is different from S. So in matrix terms, you have zeros everywhere except a 1. No, well, okay, a 1 in the S row and Tth column, okay, in row S and column T. Okay, so as usual, we consider the morphism representation, which is given by taking, I'll call it an average, although I'm not dividing by the order of G, but it's more or less the same. So there's only one representation, so that's rho G inverse, then E is T, EST, and then rho G, okay? So what do we know? This is a morphism representation. Let's call it F prime of representations. And now Schur's lemma tells me that then F prime is multiplication by a scalar. Lambda. Actually, we have seen the proof in two parts. We have seen that F prime, there is a morphism representation with, we recall this representation being irreducible, okay? It can be only of two things. Either it is 0, or it's a multiplication by a non-zero scalar lambda, okay? Of course, you can put the two together because you can simply say that this lambda is an element of C. So if lambda is 0, you get 0, multiplication by 0 being, of course, the 0 map. If lambda is different from 0, then you have a multiplication by a non-zero scalar. So which is which for this? Well, consider first the case. Consider first the case when S is different from T, okay? Then we have to decide, so F prime will be a multiplication by lambda. Would it be 0 or will it be non-zero? But so you know that F prime, say as a matrix, will be like this. Then consider a trace of F prime. Okay, and so the trace does not depend, well, of course, this does not depend on the basis. So let's see what's the trace. What we expect the trace to be. We expect the trace of such a matrix, let's say F prime, to be n times lambda. So, I mean, by considering the trace, we will know whether this is 0 because it will come out of 0, or we will know that lambda is the value of this trace divided by n, okay? So lambda is the value of this trace divided by n. Now, the trace has several nice properties. The first property is that the trace is linear. So there's a sum here, so you can bring it inside. But the other nice property of the trace is that, and we'll write it here in red, that the trace of a product AB equals the trace of the product BA. This is elementary, and of course you know it well. So this means that inside the trace, the argument of the trace, we can exchange the product. I mean, of course, normally matrix product won't be commutative, but if you put a trace outside, then you can safely exchange the two arguments, and the result won't change. So if you move this on this side, then you will get rho G inverse rho G. And of course, rho is a representation, means a morphism of groups. So this is nothing else but rho G inverse. I mean, the -1 can go inside, and then this is 1. What does it mean? That you get sum over G of a trace of is T, okay? But I'm considering first the case when S is different from T. So this means that this one is not on the diagonal. Okay, so this is 0. Actually, it's a sum. It's an order of G times 0, but of course, you'll admit that this is always 0. Because S is different from T, so this one won't be on the diagonal, so it won't count when you take the trace, which is the sum. One way of defining the trace is the sum of the elements on the diagonal. Okay, so this is 0, okay? And exactly as in the previous case then, so exactly, and in the previous result, you find that you find the zero part. Okay. Well, okay. You find well, we'll see. You find that a certain sum. Rho G inverse. So we'll see the details later. 0 and okay, with certain indices, but we'll see later. Say we see that that this is different from 0 only for a certain certain indices. But the thing becomes more interesting because in the end we are seeing exactly which pairs of indices here and here give you a non-zero result. So we'll see that at the end that all pairs of indices except the special of a special kind will give you 0. So now take the missing case. Consider a missing case, S equals T. So in this F prime, we take S equal T. Well, this time, so we have ESS, okay, which is a matrix which has exactly one non-zero element on the diagonal in the position SS, okay? So if you do the trace of F prime, exactly as we do here, we'll find that it's a sum over G of the trace of ESS, okay? This is 1 because there's exactly 1, 1. And so if you're summing a 1 over G, this will give you the order of G because it's 1, 1, 1, 1, 1 plus 1 plus 1 as many times as the order of G. And remember, this means, recall this argument here, that the trace of the lambda, this scalar, is the trace divided by n. So this means that F prime will be multiplication by lambda. This is the unit matrix. Okay, so it's this. Okay, where of course, sorry, yes, lambda, let me make a correction, where this lambda would be the order of G divided by n. Okay, remember that n is nothing else but the dimension of the underlying vector space. This is the unit. So lambda, lambda, lambda with the lambda equals this number, which is of course different from 0 because the order of G is at least 1. Okay, so we know this, and so now we are going to see what is the consequence of this. And so what we do, we take an index bk, okay, and apply this this product here. Yes, rho G inverse ESS rho G, and we'll see what happens. Well, I hope it's, well, I'll go to the next page. Let me see whether I can copy this to the other side. So let's copy this, add to the next page. Brilliant. And now let's see whether I'm able to move it. Well, okay, I'll move the whole page. Okay, so we have to develop this. So first of all, you will have, I mean, we have plenty of space. So it's sum over G of what? To Vk, you first apply rho G inverse, okay? And then ESS, and then rho of G, okay? I mean, yes, because of course this is a composition of maps and composition from left to right. So first this, then this, then this. So what's this? So this will be, we have a sum over G here, and then you'll have a sum for, well, okay, L going from 1 to N of what? I mean, you apply the kth vector to this, so you're looking at the kth row of this matrix. So you will have VL rho KL G inverse, okay? Then ESS, and then rho G. Okay, so I have applied Vk to this, and I have obtained the kth row of this, because my vectors are row vectors, so the image of the kth vector is given by the coefficients with respect to the basis are given by the coefficients of the kth row of this. So remember, this is the element of place KL in the matrix row G inverse. But then you apply ESS, and ESS kills all else, VLs, except S. And then it sends it to S. Okay, so remember, ESS sends VS. Well, okay, look, the UI are the same as the VI. I knew I was going to make this, because I mean, in the theorem, I defined the basis to be given by UI, but I'm writing them VI, but they are the same. Sorry, I should have written them VA. Okay, so VS goes in VS, and then say I goes to 0 if I is different from S. So not much survives when we apply ESS, which is a linear map, to this. It survives only the coefficient with VS, okay? And this will be the sum for G in G of VS, okay, rho KS G inverse, okay, because only this has survived. And then you apply rho G, okay? Well, so horribly written. Of course, this is just a number, so you are applying rho G to VS, and so it's exactly the same as before. You have the sum, G in G, of what? Of the sum, let's say T from 1 to N, okay, of Vt, rho K, just a second, this is KS G inverse, and then rho, I've applied rho G to Vs, so what I obtain, Vs T G is a usual fact, well, except the order. So I'm considering what happens here when I apply rho G to Vs. So I obtain the sum of this, of Vt, with this coefficient, okay? Because I have to take the S row of the matrix rho G, and then I sum over T, okay? And so what I obtain here, I obtain the sum, exchanging the summation of this Vt with these coefficients. Well, okay, and now let me do this. Since I've taken the orthonormal basis, I replace this by rho sk conjugate of G, okay? So I have taken the transpose conjugate of this, okay? Because this is This is what we can assume. Good. But remember, I had taken the element vk, and we know that this map, okay, this map, no, well, I want it in red. This map is scalar multiplication by scalar multiplication by lambda. I'll recall in a second what lambda is. So, so the point is that this coefficient will be 0 for all t different from k. Okay, because since this is scalar multiplication, the only non-zero coefficients when you obtain by applying this to vk will be the coefficients of vk. Okay, because it's on the diagonal. So what we obtain is if t is different from k, then you obtain that that is 0. Because we are off a diagonal. Is instead the t equal k, then what you've done, you apply this to vk, and you're looking at the coefficient of vk, and since this is scalar multiplication by lambda, it will be lambda multiplied by this. So this means that this coefficient, so this time s equal k, t equal k, so st, and this will be lambda, which is the order of g divided by n. And this is exactly the content of the proof, the content of the theorem, okay? Note that I didn't specify here which indices are taken here, because what we have shown in the end, that the only indices that give you a non-zero result are when, if you take the transpose conjugate here, is when st equals st. I mean, these indices here are the same here. So unless you have the same indices on this side, you get 0. Okay. So for instance, here t is different concave, which means of course that the pair sk is different from the pair st. In the other case, it's even worse because you don't have any equalities. Okay. So this is with this, we have obtained these important relations. Okay, the only way to obtain something different from 0 here is where the indices are the same, j equal L, s equal t. Okay, of course they come different in the proof, and then when they are different from 0, they are the order of g divided by n. Okay, but note that yes, okay, well, it doesn't matter. There's a technicality here, but we can safely ignore it for the moment. And now we are ready to introduce one of the main, allow me a silly joke, characters of this course. That is characters, okay? These are, as I said, a very important tool because they represent a very economical way of describing a representation. And so the idea is the following definition. Let rho from G to GLV be a representation. So, and okay, fine. And its character, this is a great idea of Isai Schur, is a map chi, usually called with Greek letters, that's chi, from G to the complex numbers, which send G to the trace of rho of G. Okay? And as I told you already, I mean, suppose that the dimension of B, this is just a convention or just giving names, is n. Okay, then to give a representation, you are supposed to associate to every element g of G n square numbers, because these are matrices n by n, okay? So to give a representation means to give n square map from G to the complex numbers. But what we will see is that knowing a character, you know perfectly well the representation. So the character uniquely determines the representation, okay? And so you're saving, say, a lot of energy or effort, because just one map from G to the complex numbers describes n square maps and codes all the information that it's in the square maps. Okay, other notation, one says that the rho affords K, so gives rise to K. Perhaps there are a couple of things to say. Chi1 is called the degree of chi of the character, and what's this? This is the trace of rho of 1. But what's rho of 1? Well, this is a representation. So this is the matrix 1, because I mean, this being rho being a morphism, a group morphism, the identity of the group goes in the identity of the linear group, general linear group, which is the identity matrix. And this is, of course, equal to this, what I call n, the dimension of V. Okay, so the degree, we will refer to the degree of chi, and this is exactly the dimension of the underlying vector space. So, of course, I mean, since we will show eventually that the character determines the representation, of course, it will have to determine the dimension of the underlying vector space, since it's going to determine everything. Well, we already mentioned this important property of the trace, which allows you to switch to the products, the order of products under its argument. And so note this fact. Well, I'll set it as a proposition in a second. Suppose we have rho 1 and rho 2 from G to GL V are isomorphic representations. What does it mean to be isomorphic? So let's recall. This means that there is this means that there is a morphism or representation which is invertible, a bijective map. Let's recall what it means that this is a morphism or representations. So we familiarize ourselves with the concept, which means that is, let's first do it on element, that is for each V in V. Recall, this is important. You apply rho 1 of G to V, and then you apply F, and what you obtain that this rho 1 of G comes out of F, except that you have a rho 2G, okay, on that side. It's the standard fact that happened when you consider those F primes, those maps obtained by averaging, so to say, averaging over the G, okay. Okay, so here, which means in practice, this is for each V in V, but of course this means, and of course G in G, for each G in G. This means that if you look just at the maps, you have this, okay? These are all maps from V to V, okay? It's a composition of maps. So this means first rho 1 of G and then F, and this means first F and then rho 2 of G. But we are here in the case where F is bijective, is invertible. So this means that you can choose what you want, but let's say means that rho 2 of G can be obtained by conjugating rho 1 of G with F, okay? Good, because F is invertible, so you are multiplying on the left by F inverse. But this means that if you are going to compute this trace, which will be the character, this will be the same as this. This being again a composition of maps, but the trace allows you to switch to the order of product here. Remember, that does not mean that if you remove the trace, you can switch the order of elements, because matrix multiplication is not commutative. But this is what happens. This property, that trace AB equals trace BA. Okay, so you can switch F with this inside the trace. Okay, and of course this cancel, and so you will find trace rho 1 of G. Why is this important? Because it tells you that when you want to compute the character, okay, you have to take the trace of rho of G. If you have to isomorphic representation, the character will be the same, okay? Because it doesn't matter whether I take rho 1 or 2, are two isomorphic objects, which from the point of view of abstract algebra are the same, two isomorphic objects being exactly the same. So what we've seen this proposition that the character of a representation only depends on the isomorphism type of the representation. Isomorphism, sorry. Which is another way of saying that isomorphic representations give the same character. It's just, what we have proved is exactly the latter fact. And I expressed it by saying that the character determines the isomorphism type of representation. This is already an advantage, because the same representation can be written in many different ways, because after all, you can simply change a basis, okay, and you get different matrices. So you might have two representations that look completely different, but then they are isomorphic. How do you know whether they are isomorphic? Well, this is just one implication, but if you have two isomorphic representation, definitely they will have the same character. What we'll see that a character determines also the representation. So in the end, we will have that isomorphism representations simply means equality of characters. This is much better, okay? Because I mean, to say that two representations are isomorphic, to show that two representations are isomorphic, in principle, means finding F. And there are how many F? I mean, there are many Fs, because changes of they are base changes, okay? But with isomorphism, which means being the same for some base change, means exactly equality of characters, which is much easier to check. You simply check whether the two characters are the same. You don't have to invent an F, okay? Just check whether they are the same. And now let's see the really important consequence for on characters of the theorems that we proved before. These are the orthogonality relations. Okay, before stating the orthogonality relations, let's introduce an important concept. Let's say, well, it's a remark. Suppose you have two functions from G, our usual finite group, to the complex numbers, okay? And remember, characters are exactly this, are of this form. They are functions from G to the complex numbers. Then, if you set, let's call it AB, this is not a pair, is this thing, it's an average, this time it's really an average, of AG conjugate BG yields is an inner product on the space of these functions. because a basis for this this is a vector space. Since the image is C, this is a vector space over C. If you do the operations on the images, and of course the dimension is exactly the order of G. So these are age. I mean, AG is the coefficient of A with respect to G. Okay, so this is an inner product. It's a standard inner product. Okay, because it is the coefficient with respect to the element of the basis, the delta G, exactly as in the group algebra. Okay, fine. So this is an inner product. It's the same thing as an inner product, say AI, BI. If you write if you write vectors as n-tuples, except that here a function like this is an n-tuple A, say G1, A, G2. Okay, where G1, G2 are the elements of G. Okay, it's the same. I mean, if you have indices, you write this, but if you write A as the n-tuple, okay, order of G tuple of its values, you get this as the standard inner product. Okay, except that I add a constant in front because this will make things better. And so it's an average really over G. So what do the orthogonality relations say? The first thing is say if chi and psi, okay, are characters of two non-isomorphic irreducible representations, okay, then their product, this inner product, will be zero. Okay, and the second thing is if chi is the character of an irreducible representation, just a second, sorry. Of an irreducible representation. I might say that if I have chi and psi that are a character of two isomorphic irreducible, of two isomorphic irreducible representation, but we have just seen that you have two isomorphic representations, then the characters are the same. So it's only one character I have. Then in this case, what do I have? I have that this inner product is one. Okay, so summing up the irreducible character, the characters of the irreducible representations are orthonormal. Okay, with respect to this inner product, to the inner product above. And we will see that they are also in the right number, so they are a basis of the vector space of function from G to C. Okay, so there will be an orthonormal base of that space. Okay, so two non-isomorphic representation, to consider characters, they are orthogonal. If you have just, say, two the isomorphic representation, there is just one character, then this is of length one, say, okay? So inner product itself is one. So how do you prove this? Well, this is quite immediate from the more general result about the components, because well, okay. So the first part is quite clear because well, okay. Okay, proof. Assume without losing generality that all representations unitary. This is just a matter of choosing a suitable basis, okay? Then in the first case, when you have two characters of two non-isomorphic representations, so suppose that chi is the trace of rho 1 of G, chi of G, and psi is rho 1, and psi of G is the trace of rho 2 of G. Okay, so they are characters of two representations. And our assumption in the first case is that the two representations are not isomorphic. Okay, so we consider the scalar product of chi and psi, and let's see what happens. Okay, we have to show that this is 0. Okay, and this is I say scalar, but inner product, but I mean the same. And so what's chi? Well, chi is the trace. Okay, so this is the sum for the index I from 1 to n, okay, this being the dimension. So they will be on two different spaces, but it's not important. Sum over 1 to n of rho 1 I, okay? The elements on the diagonal, okay? And here you will have the same with rho 2. You will have the sum, this time j 1 to m. So we are assuming that, let me write it in the right corner, in the lower corner, this goes to GLV1, where the dimension of V1 is n. And rho 2 goes from G to the GLV2, where the dimension of V2 is m. Okay, so here I will have rho 2, J, J, G. Okay, so you have this product, and so this will be, there will be an average, which is immaterial in this case. And then this product is of course, is a linear product, so it's linear on one component and semi-linear in the other, which is, you get the conjugate. Okay, so you take this out and you have sum on I and j going, I mean, from 1 to n, from 1 to m, of what? No, so sorry, yes, okay. So the sum for G in G of rho 1 I conjugate of G, rho 2 JJ of G. But this is nothing else that rho 1 I've exchanged the indices here. You cannot see because they are equal. Okay, because I assume that they are unitary, and all these are 0. Okay, that's the first result we proved. I mean, if you have the two representations which are not isomorphic, you take any sum of this kind, any indices, and you always get 0. So this is 0. Okay. So you see that all the relations that I proved before are not really necessary, but they are interesting for some other reason that we see later, and then also for a seminar you may want to, some of you who may want to take. But what's important is that you just need these indices being the same here. Okay, so this is 0.